Okay, hi guys, good morning. So today it is supposed to be math, but Nitin sir is not well, so I'll be taking it today. Right. Okay, so is everyone ready? Shall we start, guys?
Yes, sir.
Ah, cool. Right. So we have been seeing optical isomerism, isn't it? Right. So we saw what are enantiomers, what are diastereomers, what are mesomers, and I gave you certain shortcuts to find out the number of stereoisomers given the number of chiral centers, if it is even or odd, or if it is based on whether I have a planar symmetry or not, right? So all these things we saw last class, correct? Okay, so today's class, right, we'll be seeing, I told you, right, we know the number of stereoisomers now, right? But just by looking at the compound, right, with how we will be able to find whether they are enantiomers or or diastereomers or mesomers, we'll see today. Okay, right. So for that, we have to go for certain notations, right? So we are going for this RS notations. Okay, so we are going for this RS notation. So I'm going to give for the stereoisomer, for any stereoisomer for the matter, right? So I'm going to give these names R or S, right? So this R or S does not tell me whether it's dextrorotatory or lever rotatory. No, right? We know that it can either be towards right or towards left, and obviously, corresponding to that, I can have whether it is going to be dextrorotatory or lever rotatory. But this RNS notations are not going to denote that. It is just a simple notation which is going to help us find out whether that particular pair given to us are enantiomers or diastereomers or mesomers. Is that okay? Right? Okay. Now, how are we going to do it? Right? How are we going to do it? So, first thing is that you have to identify the chiral centers. Right? You have to identify the chiral centers. Obviously, you know how to identify the chiral centers. If at all you see that there is a carbon atom which has all four groups to be different, right? Obviously, that is my chiral center. That we know, right? Okay. Next, after identifying the chiral center, right? So please understand, you are going to give this RNS notation for each of the chiral center. For example, if at all you have in a molecule, there are two chiral centers, right? So for both these chiral centers, you have to give this RNS or RS basically. Okay. So please remember that it's not like for the whole compound I'm gonna give one. As many as chiral centers, as many times I do this particular thing, right? Okay. So that's the first thing, identifying chiral centers. Next, right? So you know that in the chiral center, I'm going to have four different groups, right? So for these four different groups, I'm going to assign priorities, right? I'm going to assign priorities, right? So we already know, we did this priority stuff when we went for this EZ isomerism, if you can know, but most of you were not there, right? That's the different form of cis trans, right? But anyways, again, that is almost similar, but not exactly same, right? But still, we'll be able to get this here, right? So we are going to assign priorities for the four groups. I'm going to give the numbers 1, 2, 3, 4. 1 is having maximum priority, 4 is having minimum priority. Okay, so that we are going to do. Now, what are the basis? What is the basis for giving this priority? Now, please understand the priority is going to be directly proportional, or say higher priority should be given to groups with high molar mass or molecular mass or whatever you want to call it, right? So that's the first thing. That's the thing. Basically, more priority should be given for groups which have bulky. Bulky in a sense, more weight or more molar mass. Okay, right? And after doing this, after assigning the priority, so generally the fourth priority will generally be hydrogen, because I know the mass atomic mass of hydrogen is only one, right? So generally the fourth priority will be hydrogen, right? So what I'm going to do is that you are going to make sure that the last priority, fourth priority, is away from me, right? Fourth priority is away from me. Okay, now this you don't have to worry about it, right? How am I going to make sure that the fourth priority is away from me? So basically, you are going to rotate the bonds so that the fourth priority, I'm not able to see it. It is exactly outside of the plane, according to me. It is going inside the plane, inside the plane. Okay, so I'm speaking like this, inside the plane. But you don't have to worry about it. Again, there's a shortcut for doing this. Okay, so I'll tell you what is the shortcut. So okay, so I'll tell you how are you going to do this. But before that, I will see the next point. Right. Now you have given the priorities. You have made sure that the fourth priority is staying away from me. Right. And the last step is you are going to trace from 1 to 4. Basically 1, 2, 3, 4. Obviously, you will be able to go in two of the possible ways. One, 2, 3, 4. You would have been able to go in clockwise direction. Right. Say if I put 1, 2, 3, 4. If it is like this, and this is the carbon atom, right? So what do you see? I'm going clockwise from 1, 2, 3, 4, right? Or if 1, 2, 3, 4 is like this, I would have gone anti-clockwise, right? Now this is the last step which determines whether I'm going to have R or S, right? So please understand, if you are going to trace 1, 2, 3, 4 in the clockwise direction, if you trace the priorities in clockwise directions, that means I'm going to give the letter R to this. Okay, and obviously, if I go for anti-clockwise direction, then at that time I will give the letter S to the chiral center, right? So yeah, this is what we have to do. Okay, now going back to this point, right? How are we going to do this? We are making sure that the fourth priority is staying away from me, right? Now you don't have to rotate anything, right? So whatever is there, just keep it like that, right? Now, if you find hydrogen, I would say this is one of the points. I can give it like that. So if you find hydrogen, right, pointing towards you or pointing up, right, pointing down, right? If you find that the hydrogen atom is pointing down, we know what is pointing down. Or if it is pointing towards you, okay? Hydrogen atom is pointing down, or if it is pointing towards you. Now this is the 3D structure, right? Now what if they give you Fisher's formula, right? If they give you Fisher's formula, if you find that the hydrogen atom is in the horizontal position, right? So we know up and away, vertical, towards you and pointing down, horizontal. So anyways, if you know this, you know this. Anyways, so if at all you find that the hydrogen atom is pointing towards you, or if hydrogen atom is pointing down, right? Or if it is the Fisher's formula, yesterday we saw what is Fisher's formula, horizontal and vertical, not yesterday, last class, right? So if it is in the horizontal position, in that case, you are going to reverse whatever you got. That means if at all you got R, you are going to put it as S. If at all you got S, you are going to put it as R. Any doubts? Right? So please understand, everything is done, everything you will do normally. That is, you're going to assign priorities. You are going to trace from 1, 2, 3, 4 which direction you are going. If it is going to be clockwise direction, then it is R. If it is anti-clockwise direction, then it is S. But if you find that the hydrogen atom is like this, either it's pointing towards you or it is pointing down, or if it in the Fisher's formula, if it is in the horizontal position, at that time you will reverse whatever you got. If you got R, we'll put it as S and vice versa. Okay, so these simple points, if you follow, I'll be able to give this RNS notations. Okay, now the main idea behind RNS notation, we started this is all because we have to find out whether the pair given to us is going to be mesomers or diastereomers or enantiomers. That we'll see in a while, but we'll take some examples of how to do this. Okay, right? So we will take some examples. Guys, any doubts till now? Obviously, you wouldn't have gotten any doubt unless we go for any example. So we'll go for the example, right? Okay, so let me take, I have, say, H, OH, Cl, CH. Okay, so I have this compound, right? So now I have to give RNS notation for this, right? So we don't, the first step is already done. We know what is the chiral center. There is only one chiral center here, right? So we can easily do it. Okay, so that we have to assign priorities. Now tell me, out of these four groups, which is going to have the first priority? Out of the four groups, which one will have the highest priority?
Chlorine.
Good, right? Obviously, chlorine has 35.5 as the mass. So definitely chlorine will have the highest priority. Okay, next.
CH3.
OH.
Okay, people. This is a doubt which will come definitely, right? So the thing is, now you definitely based on the groups, but what you have to understand is you have to look at the atom attached to the chiral center. So in this case, you see that to this chiral center, oxygen atom is attached, and to this chiral center, carbon atom is attached. So the like if at all you have confusions like this, right? Go for the first atom to which is attached. Now in this case it is oxygen. In this case it is carbon. Definitely oxygen has more mass, right? So definitely the second priority will go to OH. Okay, I'll tell you, there can be cases where you can have carbon and carbon here. At that time, I'll tell you what to do. But for now, in this problem, it's very simple, right? Okay, so second priority goes to this, third priority obviously goes to this, and the fourth priority goes to this. No issues, right? Okay, now we have to check whether hydrogen is a problem or not. Now, what did I tell you? Now, if hydrogen atom is towards you or it is pointing down, if it's a 3D structure, if it is a 3D structure, hydrogen atom pointing towards you, or if it is pointing down, then only have to reverse. Now, in this case, it is neither in neither of the positions, it's pointing up, so no problem. You don't have to reverse anything. Okay, so now how am I going? 1, 2, 3, forget 4. Okay, so 1, 2, 3. What direction I'm going? Am I going? What direction I'm going?
Clockwise.
Clockwise, right? I'm going 1, 2, 3 clockwise. So for this, it is R. Okay, right? So we'll take one more example. Right. Okay, this is pretty easy, guys. Any doubts? How I got R?
So
Okay, we'll take.
Ignore H.
Yeah, we just ignore the fourth priority. That's it. We don't have to worry about it. Right? 1, 2, 3 alone you do. That's it. Right? So we know when you have to reverse. There can be cases where you have to reverse. That time we'll see how to do it. Okay. So yeah, we'll go to the next example. Say, okay. Say I have carbon, hydrogen. Say I have C2H5, CH double bond CH2, and say I have a CH3. Okay, right? Fine, I have to assign priorities for this one. Okay, let me see how are we going to do it. So there is going to be confusion definitely when the competition is going to be, now CH3 is definitely the least, right? Or you can go by the normal procedures. Okay, so I have to look at the first atom to which this chiral center is attached. So carbon, 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 all are carbon atoms, right? Okay, now when I go for the next atom to which it is attached, right? So in this case, you can see that I can write it like this. Say after carbon, I have hydrogen, 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 isn't it? Right? After carbon, I have hydrogen, hydrogen, hydrogen. Okay. Now in this case, you can see C2H5. You know how is it going to look? It is going to be CH2, CH3, and this is the one which is attached to the chiral center, right? So what do I have after this? I have H, H, or say I can write it as C, H, H. Can I write it like that? I'm just telling after the first atom, like after the first atom to which the chiral center is attached. Now you can see all the things are carbon atoms. So next I have to go for the next atom to which is attached. Okay, so obviously you see this is the carbon. After that I have another carbon, hydrogen, hydrogen. So definitely which is going to have more priority among CH3 and C2H5? C2H5 is going to have more priority, or you can go by the molar mass. Okay, now when you have this kind of structures, when you have a double bond, right? Now there is some extra thing which you have to do, right? What you have to do is how do I go for it is like this. Now you can see that there is a carbon-carbon double bond. Okay, so I will be able to represent the carbon-carbon double bond like this. Okay, so you have to make sure there are two. Okay, fine. So first let me put one carbon atom, single bond. I will be able to represent it like this. Now what you understand, I have to make sure there is one more CC bond. Right, for this carbon atom there is one more carbon atom attached. For this carbon atom there is one more carbon atom attached. So I'll be able to write it like this. Okay, same way if at all I have say C double bond O. Now how will I write it? C double bond O, I can write it as C first, no problem, right? For this carbon atom there is an oxygen atom, and for this oxygen atom there is a carbon atom attached. Okay, so whenever you have double bond scenario, this is how you are going to look at it. Okay, whenever you have a C double bond C, C single bond C, you put for this carbon atom one more carbon atom, for this carbon atom one more carbon atom. Same goes there when I have a C double bond O, right? So I have C single bond O done. So for this carbon atom there is an oxygen atom, for this oxygen atom there is a carbon atom attached. No issues, right? Okay, so now tell me, keeping this in mind, out of obviously the competition is going to be between C2H5 and CH double bond CH2. Which do you think will have more priority?
CH2.
Yes, right. The double bond C will have more priority. Why? Because you can see this is the carbon atom which is attached. Right now to that carbon atom, say if this is the carbon atom, to that carbon atom, how many carbon atoms? 1, 2. So how will I write it now? I can write it as C comma C comma H. Is it not? So you can see this carbon atom, one more carbon atom, one more carbon atom, and to that there is one more hydrogen atom also. So I can write it as C comma C comma H. And what did I get there? C comma H is what I got there. So definitely the priority, first priority will go to CH double bond CH2. Right, and second priority to this, third priority to this, and obviously the fourth priority to hydrogen. No doubt about it. Right, now there is a problem. What problem? I see that the hydrogen atom is pointing down, and that's a problematic position for me. Right, so what I have to do, whatever I'm going to get now, I have to reverse it. Right, okay, so I have 1, 2, 3. I'm going like this. So 1, 2, 3, basically I'm going clockwise, right? But since hydrogen atom is pointing down, I have to reverse whatever I get. So it is not going to be R. It is supposed to be R because it is going clockwise. But since hydrogen atom is pointing down, for this it is yes. Okay, right? Fine. So we'll take a few more examples, right? Now we'll take some Fisher's formula. Okay, so let me take 2 chiral centers now. We'll see what I have to do. Right. Okay. 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 So basically, I have this compound with me, right? So just a 3D structure. Okay. So there are two chiral centers now, so you have to assign 2 times RNS. As I already told you, as many as chiral centers you have, that many times I have to go for this RNS notation, right? Okay. So we'll try to do it. Now, please understand, if at all, now in this case, you are just going to give RNS, so you don't have to number the chiral centers. But if at all you want to compare a pair, right? So at that time, you would definitely have to go for numbering of chiral centers also. For example, if I put this as 1, right? So this will have its stereoisomer pair there. So you have to understand that the carbon atom having CH3 is the first chiral center. So because if you can get RNS, and if you don't put these numbers, and if you're going to take that as the first carbon atom and do it, it is going to be entirely wrong, right? So whenever you have more than one chiral center, it is always better to give numbers. That is the numbering of the chiral center, not about the prior. I'm not talking about the priorities. I'm talking about the what is it? The chiral center number. Okay, so in this case, we don't have to do, so chill, right? Okay, so let me assign. Okay, oof. Right, fine. So in this case, what do you think is the first priority for this chiral center? What is the first priority?
OH.
OH.
Definitely, right? Why are you so less confident? Tell me confidently, it is OH, right? So first priority goes to this. Okay. Second priority.
CH3.
That's where we are doing mistake, right? So look at this. I have carbon. This is also a carbon atom, right? This is also one of the 4 groups attached. Correct. This is also one of the 4 groups attached. So if I look at this, I just have H comma H comma H. There, what I have for this carbon atom, I have I have carbon and a hydrogen. Is it not? So now tell me which is having more priority. Which one?
So the carbon atom.
Right. So see, please understand, just because like you have to please know that this is also one of the 4 groups which is attached to this chiral center. So this also has to be accounted for when you're going to go for 1, 2, 3, 4 priorities, right? So in this case, you see that carbon atom is attached with 3 hydrogen atoms. This is also a carbon atom. So I have to look at the next one. I can see that it is iodine. 1 more carbon atom is attached, and there is a hydrogen atom attached. So obviously, hydrogen, 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 iodine, carbon, hydrogen. Definitely, iodine, carbon, hydrogen will have more mass. So definitely, the second priority goes to this carbon atom, right? And obviously, the third priority goes to this. No issues, right? So now what I do, I go for 1, 2, 3. So now again, I'm going clockwise, right? So and hydrogen atom, I have to see where is it. Hydrogen atom is pointing up, so no problem, right? Because I told you, whenever it is towards you or it is pointing down, then only there's an issue. Now in this case, no issues. So if I make this as first chiral center, I'll call it as 1R. Okay, right. Next, going here to this. So definitely the first priority will go to iodine. No, don't doubt about it. Okay, so now the next competition is between C2H5 and this carbon atom, and you tell me which will be the answer. Is it the C2H5 or the carbon atom? This side.
Carbon atom, sir.
Good, right? So again, you can see for this carbon atom, I have another carbon, hydrogen, hydrogen, right? For this, what I have, you don't even have to go for it. I have an oxygen atom attached to this carbon atom. So definitely the second priority goes to this. Sorry, second priority goes to this carbon atom, and the third priority will go to this. So I'm going 1, 2, 3. So 1, 2, 3. What I'm doing? 1, 2, 3, I'm going anti-clockwise. You can see here, right? And do I have to reverse?
Yes, sir.
Yes, because hydrogen atom is pointing down. So it is supposed to be S, but since hydrogen atom is pointing down, I have to reverse it. So I'm going to get 1R, 2R. So 1 and 2 are the chiral centers number. Okay, you can even put 1 here, 2 here. There is no restriction on that. Okay, fine. So now for any compound, any chiral center, you should be able to give this RNS notations. Okay, now how are we going to determine whether a pair given to us or any of these three, enantiomers, diastereomers, and mesomer? Okay, so we'll see what we have to do. Cool. So people, let me take an example for that. Okay, actually I didn't do any Fisher's formula, but still when you go for problem solving at that time I'll do, right? Cool. So let me take an example for enantiomers. We'll see what we have to do, right? Okay, fine. Okay, so I have this, right? So let me make a mirror, right? Obviously this is going, the other one is going to be an enantiomer, isn't it? Because this is the chiral, this is the only chiral center. So definitely if I draw the mirror image, it is definitely going to be optically active, meaning that it is going to be non-superimposable mirror images of each other. So definitely it is going to be an enantiomer. Okay, so we'll see what we are going to do. Right. So if I draw the mirror image, H is still here, and you can see that the CH3 is coming like this, and C2H5 is going like this, and you have OH here. No issues, right? So let me mark the RNS notations for both of these. We'll see what we are going to get. Okay, so definitely the first priority goes to OH, second priority goes to C2H5, third priority goes to CH3. So I'm going what? I'm going clockwise, and hydrogen atom is pointing up. So no reversing. So 1, 2, 3 clockwise. For this it is R. No issues, right? So next, 1, 2, 3. I'm going anti-clockwise, and hydrogen atom is pointing up. So no problem. I'm going yes. So this is the trick, people. The trick is, if at all I have only one chiral center, for that chiral center, if you would have got an R, its enantiomer would have had S. Okay, and if at all you have two chiral centers, right? So please understand, the entire notation should be opposite for enantiomers. If you get R, I should get S for the enantiomer. If you get S, that enantiomer should be R. Okay, now if you have more than one chiral center, then what will you do? Same thing, it is going to be exactly opposite. Okay, so what and all can be the possibility? We'll check. Right, say for enantiomers, right? Say if you get R comma R, the enantiomer should have S comma S, completely different. If you have got an R comma S, you should have got S comma R. And if you got an S comma S, okay, this is done. I'll write this thing like this. And obviously, what else? What others can be the possibility? RS, RR, yeah. So I hope you understand, right? Both the chiral center, if at all you have two chiral centers, both the chiral centers should have completely different notations. Okay, now if you see that particular pair is going to be enantiomers. Is that okay? Right. So now what will we do for diastereomers? That I'll tell you. Right. So obviously we know that diastereomers are going to come into the picture only if I have more than one chiral center. If I have only one chiral center, definitely I don't have any mesomer, I don't have any diastereomer, only enantiomers are possible. Right. So if I had more than one chiral center, only then I have to go for this diastereomers or mesomers, right? So what I'm going to have is, say in the two chiral centers, one of them would be same and other would be different, right? For example, first possibility I can put it as R comma R, right? Say for if it is a diastereomer, the other one is a diastereomer, that I can have R comma S, or I can even have S comma R. Hope you understand what I'm telling. If it is S comma S completely, then it will become enantiomer. But if one of the chiral center is same, the other chiral center is different, then it is going to be diastereomers, right? Say if I have say R comma S, actually we did that. So hope you understand what I'm trying to say. Okay, say if you have S comma S, for example, right? So S comma S can be again R comma S, or I can have S comma R, right? One of the chiral centers to be different, other chiral center to be same. That is my diastereomer, right? And lastly, when I go for mesomers, everything should be exactly same, right? When I go for mesomers, if I have R comma R, I should get R comma R. If I get R comma S, I should get R comma. Again, for this only you have to be very, very careful, right? You have to make sure that you number the chiral centers. Okay. For example, if you get R comma S, and if you get R comma S there, and if you put the numbers wrong, that means they are not mesomers. They are actually enantiomers, isn't it? So be very careful. First thing you have to do is number the chiral centers. At least you you put a mental picture. Okay, this carbon atom is having CH3 and this is my first chiral center. Like that, at least you, in your mind, you keep the numbers. Okay. So people, any doubts till now? Is everything clear?
Clear, sir.
So could you just
Okay.
repeat that enantiomers part, sir? Like you've written it, I had a bit of an issue.
Yeah, sure. So enantiomers, if you have one chiral center, no problem. R means yes, S means R, the pair, right? Now, if it is going to be, say, more than one chiral center like this, right? Both the chiral centers should have opposite notation. Say, if at all I have R comma R, say 1R, 2R, right? So the first chiral center should be opposite. Second chiral center should also be opposite. So it should be S comma S, right? So if at all you get R comma S, say 1R, 2S, it should be 1S, 2R should be the notation for the enantiomer. Completely different, completely opposite is what you should get for enantiomers. Yes, understood?
Yes, sir.
Okay. So for diastereomer, one of them should be same, one of them should be different. And for mesomers, both the things should be exactly same. That is what is my mesomers. Okay, right? Cool. Now we'll take some problems for you to do. You are going to tell me the answers. Okay, tell me, what is the relationship between these two? Go for it. Yes, any answers?
Sir, first one is S, sir.
Okay, yeah, go for it and tell me whether they are enantiomers or mesomers. See, the mesomers problem will come generally, I told you, when I have more than one chiral center. But they might not be mesomers if I have one chiral center, but same compound drawn in a different way. That can also give me the same notations. Again, that means they are not mesomers, but same compound drawn differently. Okay,
So
that
both
also keep
are
in mind. Both are yes, right? So basically, what do you mean by that? That means that the same compound is drawn in a different form, different way, right? Same stereo, or not same compound, I would say, same stereoisomer drawn in a slightly different way. That's what it means. Okay. So we'll see what we're gonna do. So obviously, the first priority goes to this, second priority goes to this, third priority goes to this, right? So what I'm going clockwise, but you see hydrogen atom is in the horizontal position, so I have to reverse it, right? So definitely this is going to be S. It is supposed to be R, but since I'm having hydrogen atom in the horizontal position, so I'll reverse it. So this is S. So for this, 1, 2, 3, I'm going again clockwise, yeah, clockwise, right? Again, hydrogen atom is in the horizontal position, so I'll reverse. So they are S. So if at all they give you 4 options, right? What the relationship among these? So you should choose. They are same compound, same stereoisomer, drawn in a different way. That is the option we will choose. Is that okay? Right? Cool. So we'll take one more example. Look at this. Okay. Okay. So these two, just that one is in Fisher's formula, other one is in 3D structure. Go for it. Tell me the relationship between these two. See, there are two chiral centers. Please, in your mind, have which is the first chiral center, which is the second chiral center, same, and follow the same for the second compound. I mean, second stereoisomer. Don't mess it up.
Sir, they're diastereomers.
Diastereomers. Okay, we'll check. Any other answers? Okay, let me get one more answer, then I will do. Whether we'll see whether they are supporting your answer or they have some other answer.
Enantiomers.
Enantiomers. This is the competition I was expecting. Okay, now I will do. We'll see who's correct. Okay, so for this, definitely for, okay, please understand. So I'm going to keep in mind that the carbon atom having CH3 is my first chiral center. Okay, carbon atom having CH3 is my first chiral center. Carbon atom having C2H5 is my second chiral center. That I'll keep in mind. Okay, so fine. So first priority goes to Br for sure, right? Now tell me which is having second priority.
The other three.
Carbon.
Exactly. It is not CH3. It is definitely going to be this one because this is containing hydrogen. This is containing a bromine atom. So definitely second priority goes to this and third priority goes to this. So I'm going 1, 2, 3. I'm going anti-clockwise. Yeah, I'm going anti-clockwise and hydrogen atom is in the vertical position. So no problem. So I'm going to write 1s. First chiral center, S. Okay, next. Again, first priority goes to this, second priority goes to this, third priority goes to this. So I'm going clockwise and no rotation, sorry, no reversal because hydrogen atom is in the vertical position. So it is going to be 2R. So 1s, 2R is what I'm getting. I'll go there. Again, carbon atom having CH3 is my first chiral center. No issues, right? So again, the first priority goes to this, second priority goes to this, third priority goes to this. I'm going clockwise and hydrogen atom is pointing away. So no problem. I have 1R. No issues, right? Clockwise I'm going. For this, first priority, second priority, third priority, I'm going clockwise, right? And hydrogen atom is pointing away. So it is 2R. So what are they? They are
Diastereomers.
Diastereomers.
obviously, right? So they are diastereomers. So because you see, 1s, 1r different, and 2r, 2r same. So one of them is same, one of them is different. So definitely they're going to be diastereomers.
Sir, isn't hydrogen pointing away from us? Don't we reverse it?
Hydrogen atom pointing towards you, we reverse it. Hydrogen atom pointing towards you or pointing down, we reverse it. In this case, hydrogen atom pointing away. So no reversal. Okay, right? Cool. So one more problem, then we'll wind this up. Sorry. Okay, go for it. So this is CHO, CH2OH. Okay. Yes, any answers?
So this is diastereomers.
Diastereomers. Okay. We'll wait for one more person to give an answer.
Sir, diastereomers.
Okay. So two of you are saying the same answer. I will check. Fine. Fine. So okay. So here you have carbon, oxygen. So definitely the chiral center is attached to carbon here. It is attached to OH here. So definitely first priority goes to OH. It's all about the first atom to which the chiral center is attached, right? So the first priority goes to this. Now second priority will either be this or this. Now I have to check what is it going to be. Okay. So we already know when I have C double bond O, we know how are we going to represent it. It is going to be like this, right? So for this, how will I write? For this carbon atom, I have oxygen, oxygen, and hydrogen. For this carbon atom, I'm telling. The next atoms, I'm telling. So you can see oxygen, oxygen, and there is one more hydrogen atom attached to it. Okay. So for this carbon atom, we'll check what is happening. I have oxygen, carbon, hydrogen. For this, what do I have? Oxygen, carbon, hydrogen is what I have. And there I have oxygen, oxygen, hydrogen. So definitely oxygen, oxygen, hydrogen will have more priority. Yes? Any doubts here? How is that this is having the second priority? You want me to repeat again? Okay. So look at this. When I told you when I have C double bond O, this is how I write it. CO, OC, and again CO. This is how I write it, right? So now if I look at this, so how will I write the next three atoms for this carbon? It will be oxygen, oxygen, and there is one more hydrogen. So it is OOH. No problem, right? Now, for this carbon atom, you can see there is an oxygen atom, there is a hydrogen atom, and there is a carbon atom. So what do I put it? OCH. And what do I have there? OOH I have. So definitely that will have more priority. So the second priority goes to this, and third priority goes to this, and obviously hydrogen has the least priority. Okay, so now I have 1, 2, 3, 1, 2, 3. I'm going anti-clockwise. So hydrogen atom is in the horizontal, sorry, vertical position, so no problem. So it is 1s. Now again, I'll just look at it. The carbon atom having CHO is my first chiral center. I'll keep that in mind, right? Carbon atom having CHO is my first chiral center. Okay, that I kept in mind, so fine. Now I'll go for the second one, right? Second chiral center. So first priority goes to this. Second priority, again, I have to check, right? Now, second priority, you have competition between CH2OH and this one. So I can see I have, for this, I have OH, is it not? Carbon atoms attached to oxygen and 2 other hydrogen atoms, right? Now going there, how will I write for this? I'll write oxygen is there, carbon is there, hydrogen is there. Okay, now tell me which is having more priority. So definitely this one is having more priority. It is OHH, it is OCH. So definitely second priority will go to this, and third priority goes to this. It's looking very clumsy. Hope you understand what I'm telling, right? So I have 1, 2, 3. I'm going like this, 1, 2, 3. I'm going anti-clockwise direction, but I have hydrogen atom is in the horizontal position. So it's going to be 1s. Oh wait, I'm going anti-clockwise, so I have to reverse it. So it is going to be 2r. Okay, 1s, 2r, and the first chiral center is the one which is having CHO. Please don't remember that. Please don't forget that. Right. Okay. Now going here, see, I told you, if at all you're going to take this as the first chiral center, absolutely wrong. I have to take this one as the first chiral center because this is only having CHO. Okay. So let me do it for this carbon atom first. Okay. Fine. So first priority, definitely we already said comparing this and this will have more priority, and this will have the third priority. So I'm going 1, 2, 3 clockwise, and I'm having hydrogen atom to be in the horizontal position. So it is going to be reversed, so it will be S, right? So it should be 1s. Okay, fine. Going for the next one. So this one, I'll just take it out. Okay, so I have again first priority, second priority. Again, I know this one, that is this carbon atom. We just check CH2OH and this will have more priority. So 2 and 3. I'm going what? I'm going clockwise, and hydrogen atom is in the horizontal position. So it should be 2s. So what are they?
Diastereomers.
Okay, fine. So this is a little tricky one, isn't it? You have to be very, very careful. Okay, like it's not little tricky. You just have to, if at all you see that the carbon atom, both are carbon atoms or both are oxygen atoms, just go for the other 3 atoms to which it's attached, and accordingly you will be able to decide the priorities. Okay, right? Cool. So yeah, so now any pair given to you, you will be able to easily say that okay, these are enantiomers or mesomers or diastereomers. Okay, fine, cool. So now we'll move on. Right, we'll move on to compounds which doesn't have any chiral carbon atom. Okay, I told you that having chiral center is not, I mean, there can be compounds where you don't have any chiral centers, right? But still they are optically active. Optically active in the sense they are able to rotate the plane polarized light towards right or left. Okay, so we'll see what are all those compounds. Okay. So we are going for optically active, or say compounds without chiral centers but are optically active. Okay, so there are a few classes of compounds which can do this, right? So the first one are what are called as biphenyls. Okay, so biphenyls are compounds like this. Biphenyls. Okay, so these kind of compounds are biphenyls, but again, not all biphenyls are optically active. There are going to be certain conditions. 1 second, hold on. One second, people. Ah, okay. Okay, so I told you not all biphenyls would be optically active, right? So you have to understand that there should not be any plane of symmetry. That's definitely a criteria. Okay, there should not be any plane of symmetry, but this has a plane of symmetry, isn't it? So the thing is, they should be substituted, right? And they should be unsymmetrically substituted. For example, say I put one NO2 here and another NO2 here, and say one COOH here and one COOH here. This is definitely not optically active. Why? Because you can directly see that there is going to be a plane of symmetry, right? So how it should be? It should be like this. If at all you want it to be optically active, maybe this can be like this. Okay, so what do you see? Now there is no plane of symmetry. Okay, so they should be they should be ortho substituted, right? And they should be unsymmetrically ortho substituted. That's the main point. There should not be any plane of symmetry. Now you can ask me, sir, okay, this and all I understand, but how is it that they're able to rotate the plane polarized light? Okay, now for that you have to understand, people, this is particularly, how do I put it, say this is in one plane. Okay, this is in one plane. Now this, if you see actually the 3D structure, it is actually going to be in this plane, like little tilted plane it will be. That is how it is going to look in 3D structures. So what will happen now when the plane polarized light enters, or say now I put it like this, when the plane polarized light enters, so definitely in this plane, so there will be some kind of interaction, and definitely the interaction is going to change when it is going to come to this plane. So definitely there might be a rotation towards right or left. Okay, so that is the reason why it is going to be optically active. Okay, so what you have to understand is biphenyl compounds can be optically active depending on how the substituents are there. They should be unsymmetrically substituted at ortho positions. Okay, that is the first one. Now, other than this, I have something called as allenes. So second class of compounds are what are called as your allenes. Okay, so allenes are very simple. Allenes are these kind of compounds. When you have consecutive double bonds, these are what are called as allenes, right? Now, same reason why they are able to rotate the plane polarized light is because this is going to be in one plane, this is going to be in a slightly tilted plane. So definitely when the plane polarized light comes, it can either rotate towards right or left. But again, not all allenes are going to be optically active. So definitely if you have two hydrogens and two hydrogens and two hydrogens, no, it won't be. Okay, how it should be is the two groups attached to this should be different, AB or AB. Okay, or I can even have all the four groups to be different, A, B, C, D. Again, that time it will be optically active. Okay, and anything else? Yeah, So this one also. So these are what are called as alkadienes, cyclohexanes, sorry, cycloalkanes. So third class, right? Alkylidene, cycloalkanes, very simple. The name only is complex, but you don't have to worry about it. It's very simple. So cyclohexane, along with the double bond, I have a carbon atom. So these are what are called as your alkylidene cyclohexanes. So again, not all of them are going to be optically active. So you see that there are going to be two groups here and two groups here. Just like in that case, it should be two different groups attached. ABAB or ABCD should be there for it to be optically active. So these three classes of compounds, okay, these three classes of compounds, even though they don't have any chiral center, right, even though they don't have any chiral center, but still are capable of rotating the plane polarized light towards right or left. But again, not all of them are going to be optically active. I told you what are all the conditions. In biphenyls, they should be unsymmetrically orthosubstituted, right? And in case of allenes, you have to make sure that the two groups in each of the carbon atoms should be different, or all four of them should be different. And in your alkylidene cycloalkanes, again, this side and that side, the two groups must be different, or all four of them should be different. Okay, fine. So that is about optical isomerism, people, right? So we have started from the scratch. Now we know to the depth what all about optical isomerism. Is that okay? Right? Fine. So we are almost in the verge of concluding about your isomerism, but I told you. Okay. Any doubts till now?
Okay.
Any doubts? Any geometrical, optical, that is that structural isomerism, anyway, tautomerism, metamerism, all these things we saw. The only one type of isomerism is left, right? And that I told you, the entire isomerism can be classified into two major types, not like structural and stereo. Structural and stereo comes under one type actually. Okay, the classification can be configurational isomerism and conformational isomerism. Let me tell you that. Okay, so when I say isomers, right, we generally know the two categories we know is structural and stereo, but actually they come under same type. They come under same broad type. Okay, so I have something called as conformational. Oh, it's not. See, it's not confirm, which we say in English. It's O, not I. Okay, so conformational, configurational. Right. So under configuration only you have other two, that is your structural and stereo. No problem. This is okay. Right. So when I go for this conformational, where do they arise from? Is they arise due to rotations of CC single bond. Right. So they arise due to rotations of CC single bond. I know I told you that double bond cannot rotate. I told you how the scenario is, right? But single bond can rotate. Okay. So obviously because of that I can have different orientations of atoms. So you can see that there are going to be three groups. There are going to be three groups, right? So according to the angle of rotation, right? So there can be different orientations coming, right? So these different orientations are what are called as conformational isomers, or they're also called as conformers. Right, they're also called as conformers. Okay, so we'll take some specific examples. We'll see how this works. Okay, how much time do you have? We have almost 15 minutes. Okay, I can just give you the introduction. Good. So we're going to speak about conformational isomerism or conformers. Right, you already know it. Maybe you don't know this is what is this. Right. Okay. Now let me take ethane, the simplest of examples. Okay, Now obviously there is one CC single bond there, and that bond can rotate. Okay, fine. So now I want to represent this in 3D, because only then you will be able to understand how the orientations are different. So for 3D representations, let me use this. Like there are various ways by which you will be able to represent. One of them is what is called as your Newman's projection. Hope it rings some bell. Okay, Newman's projection, Sawhorse projection. You have studied in your 11th class, right? So you can use either of them. Okay, again, the name doesn't matter. What I'm going to use doesn't matter. Whether the orientation is what those matters. Okay, fine. So how am I going to represent this compound is, say I'm going to put a dot which represents one carbon atom, right? And I'm going to put a ring that represents another carbon atom. Okay, it's like this. Okay, first carbon atom, second carbon atom, first, second, first, second. Okay, that's the representation. So it's like the carbon atom is here, the other carbon atom is inside. That's the representation. Okay, fine. Now there can be so many millions of possibilities where I can put the hydrogen atoms. Okay, but not all of them are going to be important for me. Okay, so there are going to be two positions of hydrogens which are actually very important to me. Okay, so now I start with this. I start with the position like this. Say I have hydrogen, hydrogen, hydrogen for this carbon atom. Okay, now you can start in this the way that both the three hydrogen atoms of the first carbon atom and the three hydrogen of the second carbon atom are exactly in phase. Okay, what do I mean by that? Say this is the second carbon's hydrogen, this is the second carbon's hydrogen, and the second carbon's hydrogen. Okay, so what I'm trying to tell you is, if you look at the compound, right? If you look at the compound from this side, you should be able to view only three of the hydrogens, because the other hydrogen is exactly I would say exactly like a shadow in the other side. Okay, so when you're going to see from this side, right, you're going to see only three hydrogens, because all the other three hydrogens of the second carbon atom are exactly shadowing the three hydrogens of the first carbon atom. Okay, so like I'm going to give a name to this particular conformer. This is again as a conformer, right? So now when I'm going to rotate either of the carbon, the carbon-carbon single bond, again you'll get different positions of different hydrogen, right? Okay, so now I can say that this is like everything is shadowing everything. So I can call this particular one as eclipsed conformer, right? This is what is called as eclipsed conformation or conformer, right? So now I little rotate. Say now, like for my reference, I will keep one carbon atom stable. One carbon atom stationary, and I'll rotate the other carbon atom for your understanding, right? So obviously the hydrogen atom positions will keep on changing, right? So now, like say if I'm going to rotate it like say 60 degrees, if I rotate it like 60 degrees, the other carbon inside carbon atom I rotate it like 60 degrees. So you will get something like this. So the first carbon's hydrogen are still not changing, right? So if I rotate them by 60 degrees, so what will happen? This will come here, and this will go here, and this would have come here. So basically, you will see that hydrogen, hydrogen, and hydrogen would have come like this. Is it not? Right? So you can go for 60 degrees, 90 degree, no, 60 degree, 180 degree, 120 degree. All these will work, right? But like if you rotate them to this angles, definitely you'll get the conformer like this. Okay. So obviously this is eclipsed, right? So now in this case, you can see all the 6 hydrogen atom if you're looking from this side, right? So definitely this is I'm gonna give it a name. So this is what is called as staggered conformation. Okay, so eclipsed, you will be able to see only 3 of the hydrogens, and staggered, you will be able to see all the hydrogens, all the 6 hydrogens of ethane, you will be able to see. Okay, now the next question is, which is more stable? You tell me which is more stable.
Staggered, because it attains less repulsion.
Good, right? So staggered is more stable because obviously between the hydrogen atoms, I have least repulsion. In this case, the hydrogen atoms are very close to each other in eclipsed. So there the repulsion is more. So definitely staggered is more stable compared to eclipsed. Okay, now this is a very simple case. Now if I take butane, okay, if I take butane, what happens in butane? So if you look at this, CH3, CH2, CH2, CH3, right? So if I look at this particular CC single bond, what is the time? Fine. Okay, well, I think we can finish this. Okay, so if I look at this CC single bond, if I try to draw this kind of structures for this, okay, we'll try to do it now. Okay, fine. So can I wrap this? Hope I can wrap this part. Hope you understood this. Very simple. Okay, so say again, same thing. I have first carbon atom, second carbon atom. Now what do you see? For this carbon atom, say I have a hydrogen, and there is a methyl group here. Correct. For this, there are two hydrogen atoms and a methyl group. Correct. Same there. So now again, I can start with the positions where all the three are going to be in phase. That is eclipsed. Right. So now what I can put for the second carbon atom, H, and CH3. Okay. So this is my eclipsed. Okay. So again, I'm going to keep one thing stationary, and the other carbon atom I'll rotate. We'll see what is going to happen. Okay, so if I rotate them like 60 degrees, right? So if I do that, so let me mark this carbon atoms to be same, and what will happen? So you will see if I rotate it like 60 degree, this hydrogen would have come here, right? And this hydrogen would have come here. Oops, this is not hydrogen, this is CH3, sorry. So this hydrogen would have come here, and this would have gone here. Yes? Any doubts? This is what will happen if I rotate them by 60 degree. Correct? Yes or no? No problem? Okay. So now this, can I call it as staggered? Can I call this one as staggered? Yes or no?
Yes, sir.
I think someone is trying to speak, but I'm not able to hear.
Yes, sir.
Okay, so let me draw what is staggered. Then you will understand this is not staggered. So please understand, people. So staggered means they should be exactly opposite. What do you mean by exactly opposite is this? So say H, and CH3. Sorry, CH3. Okay, so one CH3 is here. The other CH3 should be exactly opposite. That means the CH3 should be here. This is staggered. This is staggered. Are you able to understand what I'm telling? Right? So now these two are not staggered. This and this are staggered. This CH3 and this CH3 are exactly staggered. So this is my staggered. So how will I get this? So basically this has to go another 60 degrees. So if I rotate this by another 60 degree, not 60 degree, actually it's 120 degree. Right? If I rotate by 60 degree, what will happen? This CH3 and H would have become staggered. Are you able to understand? If I rotate this one by 60 degree, this CH3 and this H would have been shadowed, eclipsed. Sorry, not staggered, eclipsed. Right? This hydrogen and this CH3 would have been eclipsed. But again, so this is perfectly eclipsed, this is perfectly staggered, and this is somewhere in between. Right? So all the structures somewhere in between are going to be called as skew structures or skew conformers, or it is also called as gauche conformers. Okay, this is again a new thing, right? So you have three types of conformers. One is what is called as eclipsed. The other one is what is called as staggered. Hope you understand this is completely staggered. CH3 and CH3 are exactly opposite, right? But here CH3 and CH3 are not exactly opposite. They are somewhere in between. So it is going to be called as gauche or skew conformation. Okay, So like, see, I can make it little more complex if I can go for 2,3 dimethylbutane. Is it not? So what will happen then? Instead of these two hydrogens and these two hydrogens, I would have two more methyl groups coming. So that will be little more, not complex, that will be little more interesting to study, isn't it? So next class we'll see that, and this conformational isomerism is actually very, very highly pronounced when I go for cyclic structures. Okay, so let me give you this thing inside of this. Say we write cyclohexane like this, isn't it? So, but in reality, it is never, ever, ever, ever going to look like this. Okay, why? I'll tell you later. And how is it going to look? Again, I'll tell you later. Okay, this is not, this is exact, or I can tell you that this is going to actually look like this. Something like this. This is how it will look, cyclohexane. Okay, so what is all this? This is what is called as chair conformation of cyclohexane. I have some other thing. I have boat conformation, twisted boat, half chair. All these things are there. So all those things we'll see next class. Is that okay? Right? So any doubts, people, in this conformational isomerism? You have to understand there are three. For straight chain compound, there are only three possibilities. First is eclipsed, another is skew, the other one is staggered. That's it. Any doubts? Any questions?
Sir, I have a doubt. So while rotating, we have to always rotate it in clockwise direction.
Doesn't matter, ma'am. You can rotate in any ways you want, but just to avoid confusion, so I rotated by clockwise direction. But if you are okay, you can rotate by anything, any direction, no restrictions.
Yes, sir. Thank you.
Yeah. Any other questions? Okay. So I suppose that there are no questions. Everybody understood everything, right? So today we learned a lot of new stuff. Okay. So please go practice, right? If at all you have gotten the books, please go practice, right? So solve previous year questions, right? That is very, very, very important, right? Yeah, that's it for today, right? Thank you.
Thank
Bye
you.
bye.
Sir.
Thank you, sir.
Thank you.